Hello everyone, this is Amirhossein Samandar. I'm a second-year PhD student at Case Western Reserve University. Today I want to talk about the effect of non-trivial topology on CMB polarization. This presentation is based on this paper that has been recently accepted in JCAP. And if you're interested, you can look at the details in this paper. This research has been done in compact collaboration. This is a collaboration that is dedicated to explore the effect of non-trivial topology in cosmology, and it includes senior professors and postdocs and grad students, and is funded by NASA. So let's start with three major symmetries in cosmology. In cosmology, we usually consider three major symmetries, which usually first one is parity symmetry, which is corresponding to a space inversion. The second one is isotropy symmetry, which is corresponding to rotational invariance. And the third one is homogeneity symmetry, which is corresponding to translational invariance. As an example of these symmetries in cosmology, let's look at the CMB map. This map is obviously neither isotropic and nor homogeneous. However, if you calculate the statistic of this map, you will find out this map is actually approximately statistically isotropic and homogeneous. So usually, in order to study this map, we consider two scalar field, which is temperature field and E-mode polarizations, and one pseudo-scalar field, which is B-mode polarization. And one can decompose this scalar and pseudo-scalar field into multiple coefficients and spherical harmonics. And in order to extract the statistics of this map, we can calculate the two-point correlation function of these multiple coefficients. And if we assume that this map is perfectly statistically isotropic and statistically homogeneous and perceive parity, and then we will these correlation functions will end up in diagonal correlation matrix in L and independent of L. And one can ask that, what if we break these symmetries and how it can affect on these correlation matrices? So in order to address this symmetry breaking in cosmology, I want to look at the non-trivial cosmic topology. Non-trivial cosmic topology is a long-lived and old model in order to explain cosmic anomalies. And a good thing about non-trivial cosmic topology is that it inherently breaks these symmetries, and it can easily affect on correlation matrices. So first, I want to just give a very brief introduction to cosmic topology. So let's start with cosmic geometry. Everyone knows that in a FLRW cosmology, the geometry of the universe can be flat, hyperbolic, and spherical. But in non-trivial topology, instead of touching the geometry of the universe, we only change the boundary conditions of the universe. The geometry of the universe can be still flat, but if, for example, we consider that we glue the opposite side of the topology box together, for example, if someone try to exit from this side of the topology, it will re-enter from the opposite side of this topology, and if that could, and it can happen for all of the side of this topology box, and then the topology of the universe would be free torus. So by just changing the boundary conditions of the universe, you can come up with different non-trivial topology. And the geometry of the universe can still be explained by FLRW. Here I am focused on Euclidean topology, which means that the geometry of the universe is considered to be flat, but the boundary conditions are different. So in Euclidean topologies, we only have 18 independent kinds of Euclidean topologies, which 10 of them are compact, and 8 of them are non-compact ones. And here is a very beautiful diagram that you can see the effects of symmetries in these Euclidean topologies. Now, I want to talk about this specific kinds of this non-Euclidean non-trivial topology, and try and talk about how symmetry breaking in this non-trivial topology can affect on correlation matrices. So let's start with the most simplest case in this non-trivial topology, which is E13 torus. In E13 torus is a compact, orientable, homogeneous by an isotropic topology. So in this topology, isotropy symmetry is broken. And you can parameterize this topology with two translations and one with three independent translations. And if you calculate the two-point correlation functions of polarizations fields, it will end up with this beautiful plot. So here I only consider the pure tensor perturbations, and the correlation matrix elements are normalized with respect to covering space CLs. Here, I use this map to map a spherical space to S map. And as you can see, you're still getting diagonal CLs in this map, which is the normal things that we will get in covering space trivial lambda CDM topology. But in addition to these diagonal CLs, we got all sorts of non-zero off-diagonal elements in BBEE and EB correlations, which these non-zero off-diagonal elements are forbidden in lambda CDM topology, which we call it covering space topology. So in general, for TT, EE, TE, and BB correlations, the correlation matrix elements are non-zero for delta L even and 0 for delta L odd. And for TB and EB correlations, the elements are non-zero for delta L odd and 0 for delta L even. But the interesting thing is that although we get non-zero EB in this topology, the parity is still we still preserve parity in this topology. So it only takes to break a statistical isotropy in order to get non-zero EB correlations, and you can still preserve parity, because that usually is a misconceptions about EB correlations. The second case is E2 half-turn. This topology is also compact, orientable, but inhomogeneous and isotropic. So in addition to isotropy symmetry, here the inhomogeneity is also broken. So we can parameterize this topology with two translations and one translation in addition to a pi rotation. So in order to the observer recognize the inhomogeneity in the universe, it needs to be off the axis of the rotation. So if the observer would be on the axis of the rotations, because it cannot see that preferred axis in the universe, it will see the universe that is perfectly homogeneous but is still anisotropic. So the correlation matrix of an on-axis observable into topology is quite similar to E1 topology. But if the observer moves from the axis of the rotations, it will end up with this off-axis observer correlation matrix, which you get all sort of non-zero elements in all the blocks. As you can see, these non-zero elements in all the blocks in EB correlations is actually a direct result of the parity violation in this case. So, in summary, if you break a statistical isotropy, you can get non-zero EB correlations. And if you simultaneously break a statistical isotropy and statistical homogeneity, you will end up breaking parity. So the necessary conditions to get non-zero EB is not breaking parity. You can still perceive parity, but get non-zero EB correlations. And here I just compared these two correlations. But another interesting thing is that although we break parity in E2 off-axis observable, but we couldn't get any diagonal EB in the correlation matrix, which is something interesting. In the third category, we want to look at the E3, E4, and E5 topology. E3 topology is we call it quathiform. It's compact, orientable, inhomogeneous, and isotropic. So The isotropy and homogeneity symmetry is broken in this topology. They can parameterize this topology with two independent translation and one translation in addition a pi over 2 rotations. So because we still have a preferred axis in this topology, but because we have a pi over 2 rotations, so even if the observer would be on an axis of the rotations, it's matter that the rotation is left-handed or right-handed, because in either case, it will end up with different places. So even for a non-axis observable, the parity is violated in this topology. The second case of this category is E for third 10, which you can parameterize it with two translations and one translation in addition to pi third rotations, which when I say parameterizing is actually means that this topology has three generators. Two of those generators are translation and one of them is translation in addition to pi third rotation. And the third case of this category is E5 sixth term, which can be parameterized with two independent translation and one translation with pi third rotation. So let's look at again to the correlation matrices of these topologies. For a non-axis observer in E3 topology, we will end up in this correlation matrix, which you can see still you get non-zero diagonal elements in E and BB correlations, and you will get non-zero off-diagonal elements in all the blocks in EE, BB, EB, and BE correlations. And for an off-axis observable, we will end up in a more interesting correlation matrix, which you can see there are more non-zero elements in all the blocks because the symmetry breaking is more extreme for an off-axis observer. However, another interesting thing is that despite to E2 topology, for E2 off-axis observer topology, here, even for an on-axis observer, you have non-zero diagonal EB correlations, which is something that we couldn't see in E2 topology. And the correlation matrices for E4 on-axis observer and E5 on-axis observer. So because of the different kinds of the symmetry breaking in these three topologies, it will end up with different correlation matrices. And still, you get non-zero diagonal elements in all the blocks. So one can ask me that, okay, you show us a lot of beautiful correlation matrices, but we all know that only diagonal elements in correlation matrix can be observed. So what about the off-diagonal elements? Or does these off-diagonal elements carry any kind of informations? So in order to address that questions, one can calculate KL divergence. KL divergence is actually means that if you have a data set and you have two distributions functions, and you want to see that can you distinguish that two distribution functions that can explain this data set, you can calculate KL divergence for those two distribution function. So if KL divergence would be greater than 1, it means that you can distinguish those two distributions functions. Here, we're interested to distinguish non-trivial topology to covering a space topology. So this expression means that we're assuming that the data set is explained by covering a space, and we want to see how probable the non-trivial topology is. So if you plot it for different topology box, you will end up with this plot. So yes, the correlation matrices are rich in informations because KL divergence is quite significantly larger than 1. But due to previous research and circle searches in Planck and WMAP, the size of the topology box is actually constrained to be larger than the size of the last scattering surface. So this part of this map is actually not interesting and is being ruled out due to previous research. And we only interested in this part of this plot, which when the size of the topology box is larger than the size of the last scattering surface, and we can easily see that it will fall off precipitatively, which means that if you increase the size of the topology box for greater than 1, KL averages drops out less than 1, and you cannot distinguish non-trivial topology to covering space topology, which is something bad. However, here there are two things. First, this is only KL divergence for tensor perturbations, which nobody can distinguish scalar and tensor perturbations in a real CMB data. And secondly, this is only for Lmax 60, and it's a very simple case non-trivial topology, and you can still change those parameters and try to come up with a more interesting observer topology box. And you can also increase this Lmax and try to add more modes into the KL divergence. So this is my ongoing research that I'm trying to exceed the limit of the Lmax and try to run this code for Lmax 150 and 200, which is a more interesting case. And that would be probably published in the following papers. And now, whenever we talk about correlation matrices, we want to see a CL plot. So this is the CL plots for E1, E2, E3 topology in compared to covering space topology. And here you can see that E1, E2, E3 topology is perfectly consistent with covering space topology. But for L less than 10, you will see some disagreement, but these disagreements are due to cosmic variance, which you cannot avoid it. And you can see the diagonal CL plot for EB correlations for E3 for a topology box of 0.8 LSS and 0.95 LSS. And why this kind of behavior is being seen in E3, 4, and E5 topology is still a mystery to us, and we will be addressed in the following papers when we try to calculate the statistic for these topologies. So at the final part of this talk, I want to talk about the observables for these correlation matrices. So for diagonal elements in correlation matrix, one can just compare it with other models, other model that predicts diagonal CL in EB correlations. Many of the most famous one is bifringes, which predicts diagonal CLs in EB correlation matrices. And we actually want to calculate the statistics and try to compare it with bifringes result. But for off-diagonal elements in the correlation matrix, we still thinking what is the best candidate to explore the effects of these off-diagonal elements. So there are previous research for these off-diagonal elements that people trying to explore the anisotropy in the Planck's and W map data. And there are some results for bipolar spherical harmonics or bipolar coefficients. So this statistic has been done for Planck's and W map data in order to find the effects of anisotropy in the universe. And you can see the expression of the bipolar coefficients in terms of ALMs and Klebsch-Gordon coefficients. So we are thinking that could be a very good candidate to explore the effects of these non-trivial and these non-zero off-diagonal elements, which all of these questions will be addressed in the following papers. And this is quite a big theoretical collaborations, and we work on a different line of research. And we hope that we come up with a more interesting results. And we recently started projects to think about the statistic of this non-trivial topology in order to do the statistics for Planck's data and WMAP data. And thank you.